Okay, so this is the first question of tier 9. A bicycle rider wants to estimate the drag coefficient of a rider-bicycle combination. So this is important. So the rider-bicycle combination. She measures the projected frontal area to be this, and the rolling resistance coefficient is this. The rider mass is 70 kg and the bike mass is 15 kg. The rider coasted down a hill that has a constant 5-degree slope. So that has a constant 5-degree slope. So you can see the angle here. This is actually 5 degree. Yeah, so this is the 5-degree slope. And it says a steady speed of 15 meters per second. You have to calculate the aerodynamic drag coefficient of this rider bicycle combination. So before solving this problem, I will quickly show you some theories actually we need to know. So far we're familiar with what is drag force, and we know the drag coefficient as well. So let's have a look. Okay, so the first thing is, I believe you all are familiar with this. So if you see this, especially when it is the aeroplane or helicopter, whatever it is, this is the total thing. The 4 different types of forces actually act here. So you see the force in to the upward direction. This is what we call the lift force. In downward directions, this is actually the weight. This is the force due to the this is in the gravitational force. This is actually the weight. The pulling force, or the moving force here, this is actually the thrust. You can see the thrust. This is kind of reaction force, which is described by Newton's third law. So every system has an equal and opposite. So when every reaction has an equal and opposite reaction, that's the Newton's third law of motion. So the thrust force is the reaction force, and you see I will get corresponding drag forces. So we have 4 different forces, especially when we'll consider the force balance. Okay, so I actually want to show you this on here. Let me just make it full screen a little bit. So what is actually the rolling resistance? So you see here the force that resists the motion of a body rolling on a surface is called the rolling resistance or the rolling friction. So if we have a car, it's moving, so this wheel, it will create, due to the friction, so this wheel actually experience some resistance due to the friction on the road. This friction, due to this rolling, it is called the rolling resistance. Actually, you see the weight due to the gravity, it is acting this direction, so the car is moving this way. So this is the pulling force, like what we said, the thrust, the reaction force for the airplane. So, and we will have another force, the drag force. That means it should be in the opposite direction. So I'm not going to discuss a lot, but the pulling force, if the pulling force is acting this way, then the gravity, it should be like this way. And here this wheel, it is rolling on the surface, so it will experience some resistance. This is called the rolling resistance. So if you do some force balance, that means for this pulling force we have 2 different force to the opposite direction. This is called the drag force and this rolling resistance. And then actually the rolling resistance coefficient, we know the rolling resistance, rolling friction. So rolling resistance and rolling resistance coefficient is different thing. So we will define this relation F equals CRN. So this CR, this is actually the rolling resistance coefficient, and F is the rolling resistance force. So keep in mind, this is the rolling resistance or rolling friction. This is the rolling resistance coefficient, and n is the normal force, which is always perpendicular to the surface on which the wheel is rolling. So you need to keep in mind this information. And sometimes we can define by using different variables, but it doesn't matter. This is the normal force which is perpendicular to the surface. Okay, so now let's move to the solution. So let's say this is the bicycle and this is the rider. So she wants to measure the drag coefficients for this combination. So and here you can see the weight force. This is actually acting this way, the downward directions, and she's moving this way. So that means the drag force, it will act this way, and I discussed the theories according to this wheel will gauge some the rolling resistance here. So yes, you see the drag force is acting this way, and this is her pulling force, and it will be the drag the rolling resistance this way, the opposite directions of the pulling force. So if we see this figure here, you can see if we draw this one, so this is 75 kg, so her mass, and the bicycle mass is 15 kg. So she's moving to this way, so drag poses this way, it creates a 5-degree angle. So this is actually the hill with 5-degree slope, and what I say, due to this wheel, she will this rolling wheel, due to this rolling wheel will get some rolling resistance. So the total reaction force here is the drag force plus the rolling resistance. So if we do some the force balance, then we can write this pulling force, it is equal to the drag and rolling resistance. Now what I actually wanted to discuss, this is very important. The rolling resistance coefficient is given 0.8 Newton per Newton per meter per second. So that's the given. So this is the rolling resistance coefficient. I showed you that formula F, it is equal CR and N, or we can say some other variable. Let's say B, velocity, because it is the normal to the perpendicular directions. So here the rolling resistance coefficient is 0.8, and we have, you say, this unit Newton per meter per second, you see. So this is actually the velocity. If we compare this formula for the rolling resistance coefficient, this is the rolling resistance. So if we want to calculate the rolling resistance by using this resistance coefficient, so we can say this is actually 0.8 and the velocity perpendicular direction. So we can say it is 0.8 b. So now let's go to the solution. So if you see here, we can write that F equals CRV. So CR is the rolling resistance coefficient, V is the velocity, and F is the rolling resistance or rolling force. So that means by comparing with this formula, we can write our rolling resistance F equal 0.8 V that I showed you earlier. So we actually don't know the force, the drag force, so we need to calculate that. So we can write the drag, we already know this formula actually. So we can write that the drag is half rho v square. This is the frontal area, yeah, that's important, the frontal area, and this is the drag coefficient. Actually we're looking for this. So you can ask me why you're calculating the drag force. Actually we need to calculate the drag coefficient, so it is associated with drag force. So that means we need to calculate the drag force. So this is half rho v square. We say this is the this is the frontal area, and CD, the drag coefficient. This is the formula actually we know. And now we know everything, the density, the velocity, the frontal area. So we can't calculate CD from here because this is one equation. two unknown. You know, the drag force is unknown and the CD is unknown. So we can't calculate the drag coefficient from here. That means we need to do something else. So what we are going to do is we'll do some force balance here. So that means, you know, the drag and this rolling resistance, it will be equal to this pulling force. So if we will calculate, we already know the rolling resistance and we will calculate the pulling force, and by doing some balance, the force balance, we'll get the, you know, the drag coefficients. So let's say I think I already said is I need to make some corrections here. Actually the pulling, you know, the drag and the rolling force, it will be, you know, equal to this weight actually, yeah, this force. So because otherwise we, yeah, this is easier for us to calculate this one. Actually I did this mistake earlier. So what I should say is this weight, it should be, you know, equal to this drag and this rolling force. So that way we'll do the force, or the, yeah, the force balance, because it is easier for us because we already know this angle. You see it is 5-degree angle here. So if we draw, you just compare this one, so it creates a 5-degree angle slope. So it's like this. So if we, this is the weight force, it is acting this way. So if we create this line, so you see this is actually the theta angle, and when we will calculate the weight, weight is actually, you know, the mass and the gravity. So we said it is wg, or you can say this is mg. Okay, instead of w you can say this is mg. So let's say this is mg or wg. When it is the force, actually, you know, yeah, so as it creates a 5-degree angles, we already know when it will be sine theta cos theta. So now I'm not going to discuss again, but when you already know for the vertical axis it should be sine, for horizontal it should be cos. So you can see the angle here. So we'll get this is the sine theta. The force is W or mg sine theta. Now if we do the force balance, you know, this is the weight force and this is the rolling resistance and this is the drag. And if we simplify this, then we'll get the CD equal 1.25. So that's it. I believe this is a very simple problem, but actually you need to know this this rolling resistance, and that's it. And then you will be able to solve this types of problem.